Okay, great.
So for the second talk of today, we'll have Marco Serra talking about the cosmological constant and dark dimensions from non-supersymmetric strings. Go ahead.
So hi everyone. So let me start by thanking the organizers for the kind invitations. I'll be presenting some work that appeared on Christmas Eve in collaboration with Emilan Dudas and Susha Parameswaran about cosmological constant, dark dimensions, and non-zero strings. Let's start with some context. So the core problem is indeed, behind this work is indeed the cosmological constant problem. As you know very well, we measure an extremely tiny dark energy scale, which is suppressed than more than 100 order of magnitudes compared to the fundamental Planck scale. And also, if we were to give our naive estimate for, let's say, a contribution from an electron, we will still fail by more than 60 order of magnitudes. So that triggers the fundamental question, why the IR physics, namely the standard model degrees of freedom, are not contributing to the cosmological constant. Now, let's come to string theory. As you know very well, at one loop, the CC is given by integrals over moduli spaces of genus 1 Riemann surface. So for the bulk gravitational contribution, we have torus amplitude. Let me just remind you that this amplitude is automatically finite in the UV, regardless of supersymmetry, thanks to modular invariance. And this is because the UV region, which is the real axis, is cut off from the fundamental domain, which is the domain of integration, thanks to modular invariance. And as in any field theory, this amplitude is IR finite as long as there are no shell tachyons in the spectrum. Now, in the presence of D-branes and O-planes, we will have three more contributions from three warships. So the Klein, the Annus, and the Mobius strips. And in particular, in our distinction, the Annus and the Mobius amplitude will set the gauge contribution to the cosmological constant, so namely the field theory contribution. And as you know very well, these three warships are not protected by modular invariance. So usually here, UV divergences appear. But as you know, we can map these divergences into the IR, thanks to the open-closed string duality. And we understand there in that channel that these divergences arises from the tree-level propagation of massless costring states, which are the so-called disk tadpole. So we can cancel these divergences, which means that from a physical point of view, in the background, the sum of charges and tensions of the objects, so D-branes and O-planes, must cancel. Now, we do not observe supersymmetry at low energies, but as we have just seen, that is not a problem at one loop in non-zero strings, provided we can cancel these tadpoles and we have non-shell tachyons in the spectrum. So the one loop CC of these theories would be still finite. But yet we have a problem, which is the so-called decoupling problem. And which means that the general expectation is that as soon as we break supersymmetry, the supersymmetry breaking scale is setting both the gauge genome mass terms, but also the gauge contribution to the cosmological constant, which means that if we want to protect the gauge genome masses, the supersymmetry breaking scale should be at least I as the TV scale, but then this is pushing the CC too far, to I. Now, very recently, within the Swampland program, there's been this dark dimension proposal, according to which the conjecture behavior of lambda in EFT consistent with quantum gravities should be that of MKK to the 4, where this MKK is the KK mass scale of a mesoscopic extra dimension, 1 in the original paper. So provided we have the right numerical prefactor, then we can match the observed dark energy scale for DD around a micron. So in the Swampland lore, this is telling us that this is small because we live at the boundary of moduli space. But of course, this is not yet a solution to the cosmological constant problem because it doesn't answer to these following two questions. So why does the IR physics not contribute to the CC, and what happened to the decoupling problem once we break supersymmetry? Now, in our work, first of all, within non-zero strings, we construct a fully fledged top-down string theory model where we realize the dark dimension scaling, and as well as we achieve the decoupling at least at one loop. This means that our model have a bulk contribution to the one loop cosmological constant, which behaves like mkk to the 4 due to the SUC breaking, a particular SUC breaking mechanism in the bulk. Whereas on the branes, which is hosting a field theory, supersymmetry will be broken in such a way that the gauge masses are tied to the fundamental spring scale, which can then be stabilized safely in the TV, because in our model, we managed to cancel exactly the gauge contribution at one loop, which means that the overall lambda goes like mkk to the 4, which then is addressing the coupling, the dark dimension scaling, and then we will have an explanation, a physics explanation for why this cancellation happens, which means indeed that the IR physics decouple. In the second part, we provide a moduli stabilization scenario for all the moduli in the compactification, and the outcome is twofold. So we will have a controlled de Sitter hilltop, where we stabilize two dark dimensions that can indeed recover the observed dark energy scale. And in the paper, we also comment on experimental bounds on the size of two large X dimensions as well as on the screen scale. So part one relies on worksheet techniques, which are mainly partition functions. So in this talk, I won't blast you with partition functions. So I will focus only on physics. So if you are curious about technical details and computations, please read the paper. Whereas part two relies on 4D and equal one IFTs. So let's start with part one, which is the string model. The first question I want to answer is why we choose to work in non-SUC strings. Well, the basic observation is that the DD scaling, so lambda going like mkk to the 4, is that of a 4D Casimir energy. And these one-loop Casimir energies are ubiquitous in string theory whenever we break supersymmetry by compactification. And this leads us to the Scherk-Schwarz mechanism. This is nothing more than an orbifold that implements antiperiodic boundary conditions for fermions along, let's say, one cycle of radius r in a modular invariant way, so according with the rules of string theory. And because of this orbifold, the gravitini 0 moles are massive, and we produce a cosmological constant at one loop, which scales like mkk to d for d space time dimensions. And the sign is given by the difference in the massless fermions and massless bosons. And this breaking is clearly spontaneous, because in the compactification limit, we recover supersymmetry. So because of this relation, then it's obvious that we can use the Scherk-Schwarz mechanism to tie the bulk contribution to the CC to this KK scale within the compactification, which can then be of order of the dark energy scale as in the dark dimension proposal. But at this point, we need to introduce a D-brane sector, which is hosting a gauge field theory that ideally would be the standard model, of course. But we soon realized that for the branes, we can't break supersymmetry using the Scherk-Schwarz mechanism, because if we do so, then what's going to happen is that mkk is setting also the gaugino mass scale. But since mkk now is set, will be set by the dark energy scale, this is leading to unrealistic gaugino masses, which means that we need the second mechanism to break supersymmetry on the branes, and that will then accompany the Scherk-Schwarz mechanism on the bulk. And indeed, string theory offers a second way to break supersymmetry, which is this Brane breaking model. So these are orientable theories where supersymmetry is broken completely at the string scale, which means that the gaugino masses are tied to the fundamental string scale. And the reason of this hard breaking is that this orientifold introduces in the vacuum mutually non-BPS D-branes endoplanes. So you can think to the easiest instance of such constructions, which is the 10D Sugimoto USP 32 model, which is nothing more than, let's say, a counterpart of type 1 string theory. So you can think of it like a type 2B orientifold with now 32 anti-D9 branes and one O9 plus brane. So if you check the charge assignments, then you see that we can cancel the charge in the background, but not the tensions. And the failure of canceling the tensions, which means that at one loop, we will have an infinite contribution to the cosmological constant, which is actually saying that the first contribution arises at tree level. And indeed, this is mimicking, this is like telling us that we have an attraction. So this is the effect of this overall positive tension. But then the problem is that this tree-level gauge contribution is set again at the same scale that the gauge genome masses are set, which is a string scale. So for our intent, which is combining Scherk-Schwarz and BSB vacua, we have two problems to overcome. First of all, we would like to have BSB vacua without dilaton tadpoles, which means that we want to cancel the overall tension such that this is going to be set to 0, and we will have then a finite contribution at one loop. But then the problem is that this contribution, despite to be finite, is again is going to be set by the string scale ms to the 4. So we face the second problem, which is again the decoupling problem. So we want to engineer a breaking such that we can cancel the gauge contribution, but still having gauge genome mass terms set by the string scale. Now, the first part, so engineering Scherk-Schwarz plus BSP vacua without dilaton tadpoles has been achieved in a very nice construction by Kudrashet, Budas, and Partuish in 2021. And this is an 8-dimensional model, which I will flash in very quickly. And that's going to be the starting point of our construction. So they start with type 2b compactified on two torus of radii R8 and R9. And then we mod by a Scherk-Schwarz orbifold. So this orbifold produces a bulk contribution to one loop, cosmological constant, which is in both either the large R9 limit or R8 and R9 large of same order, is indeed MKK to the 8, which is the dark dimension-like scaling in 8 dimensions. So R9 and R8 will be the dark dimension candidate. And on top of that, they add a BSP-like Courant default. So the outcome of these two projections is that now we have 4 fixed points, which are 207 minus S-plane and 107 bar plus and another bar 07 minus. So you can check that we need 16 D7 branes to cancel all the tadpoles. So here we cancel charges, but also tensions. And therefore, a finite contribution to one loop is going to arise in the gauge sector. Now, if you count on brane moduli stability, then these 16 D7 branes will flow on top of this of bar 7 plus. They are attracted by this plane here. And the outcome is thus a non-SUSY USP16 theory, which looks like Sugimoto model. And therefore, we will have gauge genome masses set by the string scale. But then, again, a gauge contribution, which is too huge if we want to protect the gauge genome masses. Now, this is the starting point again, as I said, to construct a model where we cancel identically this contribution. So to do that, we go to 4D, because nonetheless we want to have a 4D model, trivializing this 8D model we have just seen. And that amounts to consider a non-supersymmetric O3 orientifold that will have 64 fixed points that can be visualized as 16 copies of the 2D geometry we've just seen. So we will have 60 D3 branes, 32 O3 minuses, and then 16 of bar plus and of bi minuses. The gauge configuration we are interested in is precisely this USP8 SO1 to the 8 depicted here. So to have this gauge group, what we do is to put 8 of the 16 D3 branes on top of any of bar 3 plus. And we know that these brane moduli are stable because there's an overall attraction between the two, between the stack and the O-plane. Whereas the remaining 8 branes, one of each are placed on top of 8 of bar minus planes. So such brane, each brane will then create an SO1 gauge group for a total of an SO1 SO1 to the 8 gauge group contribution. And even if more than one branes would actually be repelled, the SO1 projection is such that this tachyon is going to be projected out by indeed the group action, which means that SO1 to the 8 is actually an overall perturbatively stable configuration. So this is a perturbatively stable configuration from the point of view of the brane moduli Now, if we start counting, for example, the degrees of freedom at the massless level, we will observe that for the USB 8 stack, we have a surplus of 8 massless bosons, which is cancelled by a surplus of 8 massless fermions from the overall SO1 to the 8 branes. Actually, if you inspect the annulus and the Mobius, you will observe that the whole spectrum is post-Fermi degenerate at any mass level. And this is a sufficient condition for the vanishing of the amplitudes themselves, which means that this gauge configuration here cancel exactly the one loop gauge contribution to the vacuum energy at any point of moduli space in the clustering moduli space. So we take any large volume limit. And remarkably, you can check that this gauge, this brane configuration is the only brane configuration in 4D that allows us to achieve cancellation of the gauge part of the cosmological constant. And the physics intuition is that these SO1 stacks are playing the role of hidden sectors, whose degeneracies are the opposite of the USB stack, which is then the visible sector that ideally would be the standard model. So this is the string theory model that we present. And at this point, since we know that the open string moduli are already stable by default, we need to stabilize the clustering moduli. And the idea is to balance the one loop Scherk-Schwarz Casimir energy, which is the only outcome of the SOC breaking in this model, against non-perturbative EFT contributions. That leads us to the second part, which is indeed the moduli stabilization within this EFT approach. So the first question is to understand which is the EFT approach, the EFT approach that describe our model. Then let's have a closer look at the Scherk-Schwarz mechanism. So at the tree level, this mechanism breaks supersymmetry such that the gravitational mass is a flat direction of a vanishing cosmological constant, because we know that the non-vanishing contribution arises only at one loop. This property here is what defines a no-scale model. And we know how to describe no-scale models in 4D n=1 supergravity in 2B, let's say. Now, in principle, there's no mass gap in Scherk-Schwarz because the gravitational mass is indeed set by the KK scale. But yet, if we integrate the gravitational in, then we can describe the tree-level Scherk-Schwarz as an F-term SOC breaking by a flux-induced no-scale scalar potential. And this is our EFT description. So the idea for the moduli stabilization is to perform a two-step procedure. We will consider a full scalar potential, which is given by a tree-level part, which is of no-scale type, plus corrections. And the corrections are given by the Scherk-Schwarz Casimir from the SOC breaking, plus EFT non-perturbative corrections, which are given by ED3 and D-1 instantons. So the first tree-level part, we stabilize the tree-level SOC directions via classical F-terms. And whereas all the flat directions of the tree level will be stabilized by this correction.
So Marco, Marco, can I just ask a question about that slide? So in your V, why consider instantons over two loops in the story?
Is instantons against one loop?
No, right. I mean, you've added instantons to one loop, but what happened with two loops?
So if we did everything consistently, two loops should be. Do you mean two loop Casimir energies?
Yeah, I mean, I guess you want to say spontaneously broken, so it's only superpotential.
Yeah. So this gonna give us a contribution.
But I would have thought Scherk-Schwarz under Scherk-Schwarz the two loop vacuum energy is not zero.
It's not zero, but it's suppressed compared to the one loop. So
it's supposed to commit to one loop, but why is it supposed to commit to instantons?
Because
it should be much bigger.
No, but okay, but we are balancing one loop Casimir from Scherk-Schwarz with instantons. So if we can balance these two, it means that since the two loop is already subleading, then the one loop, then it's going to be subleading also to the convert the instantons.
No, I think there's a basic. Okay, maybe we'll come back to instantons against anything perturbative if there's no additional loop corrections. Otherwise, it should just be loops. You should not. Who cares about instantons? It's just loops.
Yeah. So I have slides on that. So the idea is that it's like an LVS kind of stabilization. So we are balancing large volume suppression against with coupling non-perturbative. Slides on that. Maybe we can wait for them and then. Okay.
Okay. Sounds good. Thank you.
Okay. So let's start with the.
So you have 5 minutes, Marco.
And which means that we have to understand. So I'm sorry. First of all, to have all of that description, to have a for the n=1 description to be available, we need to indeed engineer an orbifold that gives for the n=1. And the orbifold that we engineer is of a freely acting Z2 prime, Z2 prime. You can find the details in the paper. I just want to let you know that this is the counterpart of the standard Z2, Z2, but we have two great bonuses. First of all, it's freely acting, so there are no fixed points. And indeed, this surface is actually a smooth Calabi-Yau threefold, which means that we only have free untwisted Keller moduli, free untwisted complex structure moduli, and not twisted at all. And the second bonus is that because the twisted sector is massive, we won't introduce any additional D707 sector, which is actually ubiquitous in this Z2, Z2 construction. And so we would avoid to spoil the cancellation that we achieved in the open string sector between D3 and O3 Brane planes. So the three-level supercality data then of this orbifold of reorientifold on such orbifolds are very well known. So we have only 7 complex moduli: the exodilaton, the 3 Keller, the 3 complex structure moduli. That's the Keller potential of STU model. And I just want you to focus that R8 and R9 are the Scherk-Schwarz, the radii of the Scherk-Schwarz torus. And R9 in particular is the directions along which we break supersymmetry. So if we want to stabilize one dark dimension, it means that the real part of T1 and T2, as well as of U3, should be stabilized at exponentially large values. Instead, if we want to have 2 dark dimensions, so R8 and R9 to be of order 1, then the real part of U3 should be stabilized at order 1. And actually, let me spoil that this is going to be the only outcome possible in our toy model of modular stabilization. Now, to start with the three-level part, we need to understand which three-level W we need to use. And the outcome is that we can mimic the Scherk-Schwarz breaking by superpotential generation, which depends on SU, 1, U2, T3, but not on T1, T2, U3. So these are our no-scale moduli, which are setting indeed the gravitational mass. Now, this is a no-scale model of a kind of odd type into B because we have a dependence of the Keller modulus in the superpotential. But actually, we know that we can get this dependence whenever we have non-geometric fluxes. So W is going to be, in this case, the extension of the GUG of phi beta and superpotential. And concretely, we will perform this flux choice such that we respect the no-scale moduli and the no-scale condition, and we also won't introduce any tadpole charges. So we can now indeed discuss the F-term conditions of this field, of the heavy ones, which then implies that some actions and the complex structures U1, U2, and only a linear combination of the real part of the T3 Keller modulus and of the dilaton are stabilized by these unbounded flux numbers, which means that, again, T1, T2, U3 are flat directions, complex flat directions, as well as the orthogonal combination of T3 and S. To lift this no-scale structure and stabilize this remaining moduli, then we we make the one loop Casimir compete against instantons. So we assume that we have a non-trivial contribution to the superpotential from D-1 instantons and ED3 branes, and against this one loop. So the one loop, this is the full modular dependence we have in these orbitals. So it's expressed by inverse powers of the Keller moduli, whereas the U3 dependence is via an essence-like series in the case of two dark dimensions, or an inverse power law in the case of one dark dimension. So that's what I was saying before. So we, in a kind of LMBS way, we want to balance the large volume suppression in the Casimir from the large Keller moduli limits against a non-perturbative suppression from the non-perturbative superpotential in the weak coupling limits.
Marco, you're now entering question time.
To proceed analytically, okay, just very quickly. So imposing the dark dimension scaling, we single out the leading order contribution to the to this full superpotential, which is given by the Scherk-Schwarz, the D-1, and then the leading ED3 instanton, which is of a two-term potential. So very quickly, I can tell you that this potential stabilizes a dilaton by its own equation of motion, and you can check numerically that it agrees with coupling. We can only stabilize U3 in the case of two dark dimensions because of the properties of this assistance-like series. So U3 is going to be stabilized to 1. Instead, in 1D case, we are left with a flat direction which persists even when subleading contributions are taken into account. Whereas the Kerr modulus, which is given by this product, is stabilized again at exponentially large values in weak coupling. So you can check that for large T, this two-term potential approaches 0 from above, which means that we have a density maximum, and this is the overall size of the cosmological constant. So it's positive and is expressed by non-perturbative term. Then if you look at stability corrections, we can lift the degeneracies between T1 and T2, and then we can also stabilize all the actions, so everything. Okay, let me just flash this slide. So we can address the Finos case that are within our solution. So if we want our solution to give the dark energy scale, using the numerical prefactor of our one loop vacuum energy, then this is possible for two dark dimensions, one of which has to be roughly 2.7 micrometers. So this table here is in the paper, and comparing this finding with experimental bounds, you see that we have a red flag. So we are violating this neutrino Barnes SN supernova 1987A bounds. And okay, let me just conclude that, okay, I will leave the conclusions here, and future perspective, you can read it and ask questions.
Thank you, Marco.
Thank you.
Any questions? Okay, we have one from Gonzalo. Go ahead.
Hi, Marco.
Hi, Gonzalo.
Yes. Thanks for the nice talk. I think this is very interesting progress. I was just wondering, it seems to me like in the end, the reason why you get zero vacuum energy at one loop in the gauge sector is because there is a cancellation between bosons and fermions in the end. So I was then wondering, in a background that breaks electroweak symmetry and gives a mass to the electron, you will presumably still generate a vacuum energy, which is the electron mass to the 4 in this setup, wouldn't you?
Okay, so let me answer to that. So what we provided is a model where the field theory contribution cancel. Okay, now
I agree.
The problem is that here, as I said here, of course we don't yet have the standard model. So interestingly, the USB8 part of the gauge group has the right rank, as the minimum rank to be broken into the gauge model group. The thing is that it's not guaranteed that this cancellation are still there whenever the central model is going to create in the open string sector. Okay, so that answer the first part answered the basic let's say question: what happened when we have a field theory? So if we break supersymmetry in the field theory, at the TV, let's say, do we have a contribution to the a TV to the 4 contribution? The idea is that no, if we have like hidden sector balancing it, of course, then we have the problem of introducing a center model.
Yes. Okay, so I guess we can say that you managed to break supersymmetry without introducing a contribution to the vacuum energy, but still the cosmological constant problem, which involves just physics that we know,
of course, it's not
still
solved.
there.
Of course, it's not solved because we don't have the center model, and mathematically we can claim the cancellation only at one loop. So higher loops could be pathological, even if there are some arguments saying that for symmetric Brane distributions, maybe one can say that this cancellation persists at higher loops. But higher loops are, again, not clear.
Okay, that clarifies things. Thank you so much. This was
you.
really very interesting.
Ivano?
Hi, Marco.
Hi, Ivano.
So I sort of wanted to go back a little bit to what Sav said earlier, which was my original question, but I think we can put it even in a simpler framing, namely, what happens to the two-loop closed string vacuum energy, right? So wouldn't you expect that generically that would be given by the string scale times some power of G string? And we don't want G string to be super small, right?
So in the closed string spector, I would expect, because of Scherk-Schwarz, MKK to the 4 times the right G suppressed.
Sorry, I meant the open string sector here, right? Yeah.
Okay, in the open string sector, the problems are higher genus. I agree with that. So
yeah,
if we found a non-vanishing MS to the 4 contribution again, that's going to be problematic. Now,
yeah,
of course, I don't have any mathematically rigorous tool to say that higher genus vanishes, of course. What I can say is that because here we are engineering, let's say, hidden sectors against a visible sector. So let me go back to this here. I will say that from the amplitudes, you would expect that higher genuses with 0 and 1 cross cap to cancel. The problem will be surfaces with 2 cross caps. On that, I don't know. Then there are arguments by Angelo Antoni and Antoniadis saying that if you have, let's say, a quite symmetric, let's say, an USP versus an hidden stack, then probably even the higher genuses with 2 cross cap are cancelled. But mathematically, I cannot say anything.
Right. But I guess what I'm trying to say is that if GS sets gauge couplings, we don't want it to be like much smaller than 10 to the minus 2. And then we need this thing to vanish to like 50 orders, 50 loop orders, not just like 1 or 2.
Absolutely, yes. Yeah, MS to the 4 is going to be problematic. Higher loops, MS to the 4 is problematic.
Yeah. All right. No, just to clarify, maybe I missed something, but yeah. Thanks a lot.
Very good. So I don't see any other questions. I think we can thank both Marco and David for their talks. And we'll see each other in 2 weeks again.
Okay, thank you.